In this video, we're going to take a look at some parent functions and transformations for exponential functions. So for each of the following, we're going to determine the end behavior of the parent function, f of x, so our b to the x parent function. And then we're going to look at the transformations done to f of x to obtain g of x, be specific, so reflections, translations, or shifts, stretches, compressions, and the like. And then after that, we're going to determine now the end behavior of g of x. So we'll see how shifting and reflections and things like that can alter what the end behaviors are, especially those horizontal asymptotes. So we're going to start with 3 to the x. So for f of x is 3 to the x. Taking a look at this one here. If we take a look at the graph of 3 to the x power, we have it right here. So we notice again that as we head to the left, our values are getting closer to 0. We looked at in the notes on the previous video. And then as we go to the right, our values grow without stopping. So for f of x, I guess I could do that in blue. For f of x, the limit as x approaches negative infinity for f of x is 0. And the limit as x approaches positive infinity, hopefully this handwriting will be a little bit better. No, not really. But the limit as x approaches positive infinity of f of x is infinity. All right, now we're going to determine the transformations done to f of x to obtain g of x. So we'll go in the same order, the recommended order. So first we'll take a look at any horizontal shifts. And for horizontal shifts, that's going to replace the x with x plus or x minus a number. And with exponential functions, that's going to be in our exponent. So we're going to start by replacing the x with an x plus 2. So if we look at f of x plus 2, we'll get 3 to the x plus 2 power. So we do have a horizontal shift. So we're going to shift. Adding is actually going to move it to the left, shift left 2 units. Next up, any horizontal compressions or reflections or anything like that. And that would be replacing our x with, in this case, a 5x. So replacing our x with a 5x is going to actually compress our graph towards the y-axis. So it is a horizontal compression. It's going to take that 3 to the x plus 2 graph. So this would be 3 to the x plus 2. And now if we evaluate f of 5x, we're going to replace the x with a 5x. That's a horizontal compression by a factor of 5. So it presses it closer to the y-axis. So it's 3 to the 5x plus 2. We don't have any multiplication by any negatives going on, so there's no reflections across any axes. But we are subtracting 1 from our function, so subtracting 1 is going to shift the graph down 1 unit, and that's going to be the result of the 3 to the 5x plus 2 and then the minus 1. So it's going to move that graph down 1 unit. So if we take a look at the graph of g of x, here's the graph of g of x. Notice now that as we go further to the left, our end behavior, our horizontal asymptote, is now at -1. So that vertical shift moves our horizontal asymptote down by that much. So for g of x, the limit as x approaches negative infinity for g of x, going further to the left, now our horizontal asymptote was at -1 because of that vertical shift. If we look at the graph going to the right, all the transformations that we did is not going to change the fact that as we go further to the right, our values keep going up forever, just like they did with f of x. So for the limit as x approaches infinity for g of x, just like with f of x, it's going up forever. So our limit as x approaches infinity for g of x is infinity. All right, part B, we have f of x equals 1.5 to the x power. So if we take a look at 1.5 to the x power, 1.5 is greater than 1, so this is an example of exponential growth, and we'll see that our function does increase as we go further to the right. So here's our 1.5 to the x, and the limit as x approaches negative infinity, like 1.5 to the negative 5 billionth power. It's getting closer and closer to 0, just like in example A. And as we go further to the right, 1.5, raising it to higher and higher powers, is going to give us y values that keep going up forever. So our end behavior for part B for f of x is the same as our end behavior for part A. So for f of x, it's the limit as x approaches negative infinity for f of x was also 0, and the limit as x approaches infinity for our function is infinity. Now let's take a look at the transformations that are done for f of x to get g of x. And for that one, we're not replacing x with x plus a number or x minus a number. Wow, that cursor got really large. So there's no horizontal shifts. There's also no horizontal stretches or compressions because we're not multiplying x by anything, nor are we multiplying it by a negative, so it's not even going to reflect it over the y-axis. But we do have this negative 1/4 that we're multiplying our function by. So the negative 1/4, there's actually two parts to that. The first part, multiplying our function by a negative, is going to reflect our function, our 1.5 to the x function. It's going to reflect that across the x-axis. And that again is a result of the negative 1.5 to the x power. The 1/4 is a vertical compression by a factor of 4. So now all of our coordinates, our y values, are 1/4 their original distance away from the x-axis. So they're 4 times closer. So we have a vertical compression because of the 1/4. We have a vertical compression by a factor of 4. Remember, your factors, we always list them out to be numbers larger than 1. So in other words, all of our y values are 4 times closer to the x-axis than they used to be, and that is the 1/4 aspect of multiplying. Again, this is a 4, so apologies if it doesn't look like 1. Hopefully now it will. There we go. All right, so we have a reflection across the x-axis, a vertical compression by a factor of 4, and we also have a vertical shift up 2. So we have a shift up 2 units, and that's just going to add 2 to our previous result. So we have negative 1/4 times 1.5 to the x power, and then plus 2. And now let's see how that affects the graph of g of x. So we'll see the limit as x approaches negative infinity of g of x, and the limit as x approaches positive infinity, so as it goes to the right. Ugh. Love this handwriting here. All right, so we take a look at our g of x. Here's g of x. Notice that now, because we reflected it across the x-axis, instead of the function going up forever, now the function, as we go to the right, is going down forever. So reflecting across that x-axis is going to have that impact. Also, this plus 2, as we saw in the last example, it did shift our horizontal asymptote of y equals 0, and it's going to do the same thing here. We have a horizontal asymptote of y equals 2. So the limit as x approaches negative infinity for g of x is going to equal 2, and the limit as x approaches positive infinity, it's going to go down forever, so that's going to be a negative infinity. So let's see how good the handwriting comes out to be. So the limit as x approaches negative infinity, as we go further to the left, our outputs get closer to 2. That's not bad. And as we go further to the right, as x approaches positive infinity, our outputs keep going down lower and lower and lower without stop. So we have negative infinity for there. So again, notice the reflection across the x-axis changes the end behavior in one of the directions, and then again the shifting up or down affects your end behavior for your horizontal asymptote for that side. All right, finally part C, we have f of x equals 2/3 to the x. So here we have a base for our exponential function that is between 0 and 1. So we'll see the graph of this is actually exponential decay. So our limit as x approaches negative infinity for f of x is going to, as we go further to the left, the graph is going to go up forever without stopping, and we'll see that in a minute. And the further we go to the right, or limit as x approaches positive infinity for f of x, this time, and we will see the graph, these values are getting closer and closer to 0. So let's take a look at that. So we'll get rid of this. And for example C, here is our graph. Notice our y values are going down the further we go to the right. So we have exponential decay. Going to the left, we're going up forever, and going to the right, we're getting closer and closer and closer to the x-axis, or y equals 0. All right, now for g of x here, we have 2/3 to the negative x minus 5, so we don't have any thing we're adding or subtracting here, but we do have some issues here. We have, first, we're going to replace this x with an x minus 5. So when we go and replace 2/3 from x to x minus 5, that is actually a horizontal shift. And minus, remember, horizontal shifts actually go the opposite way of where we think. This one's actually going 5 spaces to the right. So we have a shift of 5 to the right. And we can actually see that in the graph. So if we do, let me just get rid of this here for a moment. And notice again, it did shift our graph 5 spaces to the right. Might be easier if we kind of zoom in here. So we do have 1, 2, 3, 4, 5 spaces to the right. And now we're going to replace this x with a negative x. And replacing x with negative x, that is a reflection across the y-axis. So it's going to take this previous graph that we just typed in and reflect that graph across the y-axis because we're replacing x with a negative x. So that is a reflection across the y-axis. Ugh. I hate writing on these tablets. Good enough. So we'll see. Maybe we want Chrome here. If we replace this x, it's going to take this graph and flip it over to y-axis. So we're still going to have this point, but now we're going to flip it over to y-axis. And there it goes. So now notice with that reflection across the y-axis, now it's a model of exponential growth. So it started out with exponential decay, but by flipping it over the y-axis, we now get exponential growth. And the reason for that is, if you look at it as 2/3 to the negative 1 power here, that's a reciprocal of 2/3, which is 3/2, which 3/2 is exponential growth. So that's the mathematical reason behind that, but we can see it from the graph. So we don't have any vertical shifts, so our horizontal asymptote is going to go to 0 here as x gets more and more negative, and it's going to go to infinity as x gets more and more positive. So for g of x, hopefully the handwriting's good here, the limit as x approaches negative infinity for g of x, that one is getting closer and closer to 0, and the limit as x approaches positive infinity for g of x is going up forever, which is infinity. So, all right, that about does it for this video. Thank you for watching.